Welcome back, everyone, for the final masterclass session brought to you by Master Hydronics. Industry legend John Siegenthaler is here to share insights on designing a dual fuel system, adding a heat pump to a boiler system. I'd like to thank our sponsor for this keynote presentation, and that's IBC Boilers. With no further ado, John, the stage is yours.
Always great to come up to Canada. I say that with sincerity. I'm from your southernmost province. It's called the United States, America. Yeah, I know. We're still friends in this room, right? No, seriously, I commend all you folks in Canada during the day and talking to different people. We have nothing like this in the U.S. We have no conferences or programs where people that are doing hydronics can get together, look at hardware, learn, obviously, about different techniques and so forth. So the Canadians, in my impression, you've done an excellent job, and keep it up. I really enjoy coming here. I've got a lot of friends that I'd love to see up here. So let me get into it. We're going to talk about adding a heat pump to an existing boiler system. Just so I, again, get a feel for the audience, how many here have worked with air-to-water heat pumps? Some of you. Okay. Keep your eye on air-to-water heat pumps. They are going to become I feel, a very strong component in the overall hydronics market going forward. Some of that is due to what they can do that boilers can't do. For example, cooling. Obviously, we've got electrification programs down in the States, New York State in particular. At the end of this year, any new construction, starting in 2026, any new construction under 7 stories or less, no fossil fuels. Now, I disagree with that. I think that's incorrect. I've also interacted with people, and this is one of the reasons we want to do this session, that the only way I can say it is they despise fossil fuels. And that's the wrong attitude. Heat pumps and boilers can work together very well, and there's a very complementary relationship. And we're going to get into some of that today. And I've got 45 minutes, and Doug's going to have a hook here. He's going to pull me back at 46 and a half minutes, okay? So these are just some of the topics we want to talk about. Very briefly, if you haven't worked with air-to-water heat pumps, we're going to do a very quick intro of that. We're going to talk about the performance characteristics. I'll show you how they perform in a cold climate based on simulation studies that we've been part of. And I'm going to try to justify why it makes sense to keep a boiler in an existing system or even use a boiler in conjunction with a heat pump in a dual fuel application. We'll talk some piping arrangements, and I'll show you some examples. So before we get into details, okay, this probably should be obvious to anybody in this room, but we see it happen. Don't try to add a heat pump to a hydronic system without first understanding hydronic systems. And I've seen this over the years that I've worked in hydronics. A new fuel source or new energy source will come along. It could be a wood boiler. It could be a heat pump. It could be a solar thermal collector. And people get very excited about this new heat source, like it's going to solve all our issues. But they don't want to spend time analyzing the existing piping. They just assume they could cut the boiler or whatever it is, the existing heat source out, drop this new heat source in, connect 2 pipes, turn it on, everything's going to be fine. And it isn't. And I think most of you in this room that have had any experience with hydronics understand that. It is a system. It's like dropping a Ferrari engine into a Cub Cadet lawn tractor and showing up at a NASCAR race. Okay, I use that analogy. So, and secondly here, adding a heat pump to a poorly designed, installed, or improperly maintained hydronic system will not fix the existing problems. So you've got to look at it. You've got to put the patient on the table and really do some examination before you just say, yes, we can just drop a heat pump into this project and everything's going to be good. Again, these should be obvious, and I think they would be to most of you in this room, but they aren't always obvious to a homeowner. They get excited about the new technology. Can you add an air-to-water heat pump to my system? Well, probably, but let's take a look at the system first. So I put that down. One of the reasons I believe air-to-water heat pumps are going to be a strong component in the future, they're a way to electrify existing hydronic systems. And again, in the States, many energy programs are pointing towards electricity. Again, some of them are, I feel the time frame is a bit unrealistic in the goal, but in general, the market is moving in that direction. And I'm assuming that's true up here, probably more so in Eastern Canada than out here. But still, do you have electrification targets here in Alberta? You do, okay. So, that market is, that is where the energy markets are going to tend to go. So we need, in our industry, we need a solution, especially when it's a case where how do I electrify an existing system, okay? Now, everybody here is familiar with ductless systems. They're everywhere, so you can buy them online. They work. And I think most of you would be familiar with geothermal heat pumps, and in the hydronic applications with geothermal, typically it's going to be a water-to-water heat pump. The ductless system is air-to-air. So what we're doing with an air-to-water heat pump, we're essentially saying, all right, we're going to use the air side technology to gather heat from outside air, but we're going to distribute it using hydronics. So it's really not exotic technology. It's not as if there's something about an air-to-water heat pump that we've never understood before. It's simply merging an air source refrigeration system with a water side distribution system. And internally, real quickly, I don't want to spend a lot of time going through it, but I think most of you would be familiar with a basic refrigeration system. In the case of an air-to-water heat pump, up there at the top, we've got an evaporator coil with a fan. That's where we're blowing outside air past the coil. We're absorbing low-temperature heat. We're causing the refrigerant to change from a liquid to a vapor. We're sending that down through a compressor. The compressor is compressing the vapor, driving up its temperature, driving up its pressure. And now we're going to send that high-pressure gas, high-temperature gas, through another heat exchanger. We're going to transfer heat from the refrigerant to the water, and that's going to carry it through the remainder of the distribution system. And then finally, we've got some type of an expansion device that will restore the condensate or the condensed refrigerant back to a state where it can go back up through the evaporator. And the component I didn't mention there is the reversing valve that's been around for decades. Just about every air-to-water heat pump that is intended for space heating or cooling applications is going to have a reversing valve. Now, there are air-to-water heat pumps that are just designed for domestic water heating. So they're heating-only devices. They don't have reversing valves. But when you're buying an HVAC heat pump, it's pretty much, I would say it'd be very hard to find one on the market today that doesn't have a reversing valve, meaning it can do heating and cooling. So the cooling cycle essentially swapped the functions of the air coil. Air coil now is dissipating heat to the outside air. The refrigerant to water heat exchanger is chilling the fluid that would then get pumped through some type of an air handler or some other type of terminal device in the building. They come in different flavors, different physical configurations. I say by far the most common current configuration in our market is a monoblock heat pump. And that simply means that you're buying a heat pump that is self-contained. It's not a split system. It comes with the refrigerant already installed in the device. This is going to be the form factor that I think is going to be the strong initial market for air-to-water heat pumps. That being said, there are other forms we're going to look at, but a monoblock is a common type of system. One of the advantages of the monoblock, because it is a self-contained system, it has the refrigerant in it, the installing contractor doesn't necessarily have to have the tooling or the skills to deal with refrigerant. So you don't necessarily have to have refrigerant gauges, vacuum pumps, that type of thing. That being said, I would strongly encourage anybody, if you've come from essentially a water side background in this industry and you want to get involved with air-to-water heat pumps, you need to learn basic refrigeration. You need to learn how to service the refrigeration system in that heat pump. Eventually, like any mechanical system, there could be a problem with the refrigerant system. And you don't want to be in a position where there is a problem with something in the refrigerant system and you don't know how to service it. Got to call somebody else to take care of that. That's a quick way to discourage further use of that type of technology. So learn basic refrigeration and tool up to do things like recover a charge, change a filter dryer, something like that. Just some examples, what they look like. These are examples. These have been around in the North American market for several years now. And then the next slide I want to show you is this. This is back at the 2024 HR show. Many of the well-known brands in boiler technology, the IBCs, NTIs, Weil-McLean, Burnham, Viessmann, Lochinvar, they're all offering air-to-water heat pump systems now to round out their offering. Now, they aren't doing that just to cut their boiler sales. They're doing that to enhance their boiler sales. And again, dual fuel application, a lot of merits to it. I just wanted to show you that availability of product in the market right now is not a problem. There's at least 18 companies in North America, and I can assure you more coming within months, if not, 2026. You're going to have plenty of product availability to work with. Here's another case. This is called a hydrosplit system. A hydrosplit system is the monoblock outdoor unit paired up with an indoor box. I'll call it a hydro box. The hydro box would have the circulator. It would have valving. It would have controls. It will have purging valves. It may have an electric booster heater. Essentially, the components that you would buy and individually put together in the field, the manufacturers that are offering the hydrosplit systems, they're pre-engineering and pre-assembling these components. And the idea is you're going to hang this box on the wall, and essentially, as an installer, you're going to be running piping from this box to the monoblock heat pump. You're going to run piping to your distribution system. You're going to run piping to your indirect water heater. So they're trying to do two things. They're trying to avoid design errors by pre-engineering the system. And secondly, they're saving you time in the field by pre-assembling as much of the system as practical into this box. So that's a hydrosplit. And then the other split, I'll call it a refrigerant split, or sometimes you'll use the term DX, direct expansion, meaning refrigerant. This has an outdoor unit and an indoor unit, but they're connected with refrigeration line sets. So there is no water in the outdoor unit. That is an advantage, certainly in terms of freeze protection. You don't have to use antifreeze in the system. Most monoblock applications today, the majority of them are going to require antifreeze in the system. There are other components on the market. There are freeze protection valves that will open at near freezing conditions, drain water out. I don't want to go too far into the weeds on that, but they are out there. But freeze protection obviously is important if you're going to have an outdoor unit and you're bringing water to it. Many of the monoblock heat pumps will periodically turn on the circulator for a period of time, even when there's no call for the heat pump to operate. And what they're trying to do is they're scavenging heat from the rest of the system to keep the water in the outdoor unit above freezing. And it works, except in a power outage. So if you have a long-term power outage, unless you can drain that water, obviously, sub-freezing conditions, 2 days without power, it's going to freeze. So a DX split system does require refrigeration, basic refrigeration skills. You're going to have to install the line set, pressure test it with nitrogen, do the vacuum pump, and typically the outdoor unit comes with a pre-measured amount of refrigerant in it. Once the line set's in place and it's evacuated, you're going to open a couple service valves, the refrigerant's going to flow into the system, and you're ready to go. So those are the three flavors or variants on the physical configuration of an air-to-water heat pump. Now, performance. One of the people that also talks about using air-to-water heat pumps in the market uses the term, heat pumps are not boilers. And it's a simple phrase, but it's very important. When we think about a boiler, we think, it has a certain heat output rating. We turn it on, and it operates at that capacity. I'm talking about conventional boilers, not necessarily mod-cons that can modulate. With a heat pump, the heat output is very dependent on two things: outside air temperature and leaving water temperature. The colder it gets outside, if you look at the graph there, you'll see the bottom axis is outdoor air temperature. And those three lines or curves that come down, it shows you how the heating output of the heat pump decreases significantly as you go to lower and lower air temperatures. It also decreases as you go to higher water temperature requirements. There is an exception to that, and that is heat pumps with vapor-injected compressors. I'm going to show you that in a minute. But in general, heat pump theory, the colder the air is outside and the warmer the water you're asking the heat pump to produce, the lower its heating capacity is going to be. And it's the same story with coefficient of performance. How many here know what COP stands for? How many have never heard it? Seriously, just let me show of hands. Okay, COP is the efficiency of a heat pump. It's output divided by input. The higher the COP, the more efficient the heat pump is operating. So we're always trying to design our systems to enhance the COP of a heat pump. To give you some numbers, an air source heat pump, if you look at that graph there, if it's warm outside, if it's 50 degrees Fahrenheit, I apologize, I still use Fahrenheit. Metric is a better system, but from the States, it just hasn't made much of penetration down there. So at 50 degrees and that lowest curve there, 110 degree leaving water, we're going to have a COP over 3.5. And I've heard it described as 350% efficient, or 3.5 times as much heat output as you would get by taking the same amount of electrical input to the heat pump and just dissipating it through an element, the heating element in a tank or any type of electric resistance heat. But if I look at the other extreme, if it's minus 10 degrees Fahrenheit and I'm asking the heat pump to do 130 degree water, my COP is more like, looking at the graph from here, about 1.8. So that is a huge change from optimal conditions. So keep in mind that heating capacity and efficiency, expressed as COP, it's constantly changing. It changes literally minute by minute. If your water temperatures are changing or your outdoor air temperatures are changing, certainly over a period of an hour or a day, you can have significant change. And that's really not true to any extent with a boiler. So how do you size a heat pump to a load? Well, we're going to get into that. Now, over on that far right, the cloud diagram there, that blue cloud represents anything you're extracting low temperature heat from. In the case of air to water, be outside air. The red cloud represents what you're putting the heat into. With an air to water heat pump, you're putting it into water that's going to go heat a building. Anything that brings those two clouds closer together is going to improve both the heating capacity of the machine and the coefficient of performance. Now, we can't do much about changing the outside air temperature, but we can, as designers, affect that leaving water temperature requirement. And the bottom line is simple. The lower your distribution system can operate in temperature, the better the performance of the heat pump. So it is important to design around low temperature distribution systems to maximize the performance of a heat pump. And there are things you can do to existing systems to bring the water temperature down. Again, I'm hoping to get to it. Now, there's a vapor compression cycle. We've talked about this already. Okay, that's the basic one. Over on the right, that is what's called enhanced vapor injection, or just a vapor injected compressor. And without, again, getting too much into the weeds, what we're doing with a vapor injection refrigeration system, we're taking the liquid condensed refrigerant from the condenser. Now, this is the the refrigerant that has just given up heat to the water stream going in the building, and instead of sending that directly to the thermal expansion device, we're going to send it through another heat exchanger. And that little heat exchanger that you see right there, that's called a subcooler. And the function of that heat exchanger is to lower the temperature of that liquid refrigerant as low as possible before it goes to the expansion device. And again, what it does in a nutshell, it allows the heat pump to work at lower outdoor ambient temperatures by cooling the refrigerant to a deeper temperature. Literally, we can have refrigerant as low as minus 40 degrees. And I guess at minus 40 degrees C and degrees Fahrenheit cross, right? So imagine refrigerant at minus 40, that would allow you to absorb heat from very cold outside air. And there are heat pumps now that talk about operating at like minus 20 degrees Fahrenheit. So very, very cold ambient conditions. Now, yes, they can operate at those temperatures. The COPs are really not good, and neither is the heating capacity. The machine is still running. It's going to give you some output, but that's where the supplemental heat output from the boiler comes into play. So that region, what we're looking at there are just temperatures of refrigerant. So again, bottom line, vapor-injected systems are being very common today. You'll see a lot of the monoblock heat pumps that are out there have vapor-injected compressors, variable speed compressors. How do you know? If you're looking at a vapor injection system, you can look for the subcooler, look for that little brick-size heat exchanger, secondary to the main heat exchanger, and also look at the compressor. You'll see there's 3 pipes going into the compressor. Part of doing a vapor-injected refrigeration system is taking an intermediate refrigerant gas and returning it to a certain specific location in the scroll set on the compressor. So you see 3 pipes going in the compressor, you've got a vapor injection system. Now, when it comes to how well do air-to-water heat pumps perform, the only way to really know how they're going to perform is you have to define the building, you have to define the climate, and you also have to define the performance characteristics of the heat pump. So those curves that I was showing you for heating capacity and COP, basically we put it all together with a computer-based simulation. We would run a building with a given heating distribution system in it, a given heat pump, and a given climate. We will run that through hour-by-hour simulations, or using what's called bin temperature data. We would run it through a complete heating season. And what we're looking at is how it's performing at every small increment of outdoor air temperature and small increment of changes in water temperature. So collectively, we're integrating that seasonal performance together. And we've developed some software to do that. We did a project in New York State for an organization called NYSERDA, New York State Energy Research and Development Authority. And I just want to share some results with you. I'll start on that far left column over there. That's the water temperature required by the distribution system at design load. And it ranges from 100 all the way up to 180. And then the red column, let's see, I could read it from here. Seasonal average COP, no domestic hot water. Let's say we're running the simulation. We're not including domestic water heating in the simulation. That's the blue numbers over on the right. Well, you can see, and there's a little glare here for me to read it, if I had a given heat pump, and this was based on a non-modulating monoblock heat pump with a vapor-injected refrigeration system, if I have a low temperature, like a radiant floor system that could operate at 100-degree water at design load, the seasonal COP for that heat pump was about 2.8. That's a pretty decent number in a cold climate. By the way, this was run in a very cold climate. Anybody know where Plattsburgh, New York is? Probably not. Jill, you do. It's way, way up at the farther tip, northern tip of New York State, right below Quebec. And it's about 8,000 degree Fahrenheit day climate, -9 Fahrenheit design. It's a cold place. And again, as we go up in water temperature on that first column, you can see the COPs are dropping down, but you can also see the percentage of the seasonal space heating load that the heat pump is supplying. Now, I should tell you, this is a nominal 4-ton rated heat pump, 48,000 BTUs per hour. If you've never heard of the term ton, it's not the weight of the heat pump, it's 12,000 BTUs per hour. So when we say a 4-ton heat pump, we're talking about a machine putting out 4 times 12,000 BTUs per hour, 48,000. We're going to put a 4-ton heat pump in a 3-ton building. The building that this simulation was based on it had a design load of 36,000 BTUs per hour. That's 3 tons. And I'm sure some of you are thinking, well, you grossly oversized the heat pump. You're thinking like a boiler now, okay? Remember, that 4-ton heat pump is only 4 tons at certain outdoor conditions, favorable outdoor conditions. Under a complete seasonal simulation, there's going to be times that heat pump could only put out maybe 1.5 tons at sub-0 degree Fahrenheit conditions. So this simulation factors all this in. And we ran, I want to jump to a graph. Those 3 curves there, those show you seasonal average COPs, 3 climates in New York State, all the way from the northern tip in Plattsburgh, very cold climate, to Albany, mid-climate, midway down the eastern side of New York State, and then down into the city in Brooklyn. And of course, you have drastically different conditions, and these curves reflect what's going to happen. You'll see that between 100 and 120, most of these curves are relatively flat. That's a good water temperature range to work in, okay? But as we start to push the water temperature required at design load to higher values, you see the curves come down. But they're still relatively good performance. And we did not want to sugarcoat these simulations. We built in corrections for things like defrosting. Air-to-water heat pumps have to defrost just like any air source heat pump in a heating seasonal climate. So that gives you some idea that obviously warmer climates, higher average seasonal COPs, and lower water temperatures enhance the COPs. And the last graph here, this is the percent of the space heating energy that the heat pump could carry. And again, this is a generously sized heat pump. It's a nominal 4-ton machine in a nominal 3-ton design load situation. We're carrying upwards of 90, in some cases 95% of the seasonal energy. And you know, this makes a good point. The people that are very, very strong advocates of saying you've got to get rid of the boiler in order to put the heat pump in. And believe me, those people do exist, okay? They don't want anything to do with fossil fuel. We came very close to having a state regulation that as a prerequisite for any rebates on air-to-water heat pumps, the existing fossil fuel boiler had to be ripped out. And I said, don't do that. And I'll support that. But if you can cover 90 to 95% of your seasonal space heating energy, would you give me 5 to 10% through the fossil fuel system? Okay. I think most people in here think that's a reasonable thing to do. Anyway, why do we want to keep the fossil fuel boiler in the system? Well, we've just talked about heat pumps aren't constant output devices. The colder it gets, the lower the heat output. When it's very cold, we need supplemental heat. If we're retrofitting an air-to-water heat pump to an existing system, look at the boiler. Has it got design life left in it? Okay? If it does, I would not advocate removing it. I would rather modify the system to keep the boiler in place, use the air-to-water heat pump as your first stage of heat input, and then use the boiler as the backup. Okay? So we need it as supplemental. We also need it as backup. Heat pumps today are fairly sophisticated machines. There's a lot of electronics. There's a lot of sensors. There are things that can cause error codes and the machine will shut down. And if it's a component failure, this is the question you want to ask. As a reasonable homeowner who has had somebody in this room install an air-to-water heat pump, let's say some sensor simply stops working. Temperature sensor, pressure sensor. There's some kind of an error that they shut the heat pump. What's a reasonable expectation for service? Should it be serviced by the end of the day? Should it be serviced by the end of the next day? Is the replacement part a day away, a week away, or a month away? Okay, that's important right now as these products come into the market. Remember, many of these products are not built in North America. They use things like, for example, 240-volt circulators that are built into the product. Now, I'm not trying to downplay the product. I'm simply saying as a technician, as a supplier, you need to think about replacement parts, just like you would with any other product. If you're carrying a line of boilers, you likely have access to service parts in relatively short period of time. I think that's very important as this market, it's a fledgling market right now. As it grows, we need to make sure those those heat pumps can be serviced. So if a heat pump goes down and the part is a week away, obviously that boiler is going to be a godsend in that system. I'm going to go rapid fire through these. Oop. You may avoid the need to upgrade the electrical service. Now, one of the things you're going to look at when you go in and consider an air-to-water heat pump, look at the service panel. Is it a 200 amp panel? Is it a 100 amp panel? If it's a 100 amp panel and it's full of breakers, you're probably going to have to upgrade the service to run a heat pump. Certainly if you're going to put 6 or 9 kW of electric resistance backup heat on that heat pump, or if that backup heat is already built into the heat pump system that you're going to install, typically you're going to have to upgrade that service. And today, anybody bought a coil of 12.2 Romex lately? I bought a 100-foot coil of 10, what was it? It was 10.2, a 100-foot coil of 10.2 Romex, I call it, or non-metallic sheath cable. Let's see, I bought it at Home Depot. It was $216 US for 100 feet of number 10 gauge cable. Wiring is expensive today. So again, having a boiler might avert a need to back it up. Certainly if it displaces electric resistance backup, using fossil fuel as the backup, you don't have anywhere near the kW requirement to run that boiler. How about this? We can run a burner, if it's an oil burner or gas burner and a few circulators, we can run that on that little generator over there on the left. You can buy it at Harbor Freight for $600. I would encourage you to design your electrical systems today so that the homeowner can flip a switch, a transfer switch, and simply move the boiler and the components you need to power for the distribution system to an emergency generator. You could probably run an oil burner and a few circulators less than 1 kW, and that little tabletop generator is about a 2 kW output. So simply allowing the homeowner to flip the switch over to the generator, you plug in the generator, and as long as you've got gas in the generator, they've got a heating system that's operating. Now, can you do that with a heat pump? Can you run a heat pump with a generator? Well, you can't run it with that little generator there. You're going to need more like the Generac or a Kohler or other brands. You're going to need a much larger generator, much more expensive. So this concept of resilient design, I'm sure that word has made it up here. It's used all the time in the States. The idea that under a long-term power outage, there's a way to keep this system operating. And it's a good concept. It's a good concept. So again, it could be very simple, wiring up the system so a transfer switch could move the boiler and the distribution system to your backup generator. If you're going to tear out the boiler, look at what you got to do, especially that middle photo. I don't know about up here, but underground fuel oil storage is a no-no, in my opinion. But there are a lot of fuel oil tanks in the ground in the area where I live. And it's very expensive to take them out. And if they leak, you're going to lose the house. It's tens of thousands of dollars to clean up the mess. Why go through that? Why? Well, I would tell you, I would decommission any outdoor oil storage tank, especially an older one. But the idea that you're taking out the boiler, you're taking out the chimney, the flue, the oil tank, and all that, it just adds cost to the project. If it's got design life left in it, design around it. Okay. Now, load shedding by utilities. This is going to become more and more of a factor as we go forward. Utilities trying to meet electrification targets today, they're going to get more creative with rates. I understand you have flex rates up here, or off-peak rates. We're seeing more of that in the States as well. So the idea that the boiler might be the preferred heat source when you're at peak price for electricity, and the heat pump may be the preferred heat source when you're at minimum price for electricity. So the ability to coordinate these heat sources so that you're basically giving the owner the lowest overall heating cost is another argument to keep the fossil fuel boiler in the system. And quite honestly, there may be systems where heat pump technology today with R410A, which by the way, in the United States, that ended in January of this year. They cannot manufacture 410A based heat pump systems in the States after December 31st of last year. The market has moved to R32 and R454B. I think within 5 years, you'll see R290. Anybody know what R290 is? Propane, not as a burn of combustible fuel, as a refrigerant. Very low global warming potential, of environmental, people love it. And it actually is a really good refrigerant. There's only one little problem. Kaboom, yeah. So these heat pumps have to be designed to make sure that if there is any kind of a propane leak, they can sense it and they shut down. But you may have loads that simply current day heat pump technology can't supply. If it's an old indirect with a scaled up coil on it, 140 degrees might not give you the proper heat transfer through that coil. So you may have a load situation due to existing constraints in the system where you simply have to supply water temperatures beyond what the heat pump can do, okay? And here's the one that I think is really going to be important for the hydronics market going forward: time of use electric rates, coordinating air-to-water heat pumps with thermal storage and time of use electric rates. There's some really interesting stuff taking place, some research projects right now in the US, and I've been privy to see some of these results, and I'm impressed by the results. Imagine taking a house built in the 1950s in Maine, Millinocket, Maine. Anybody know where Millinocket, Maine is? Didn't think so, okay. It's a little town way up in northern Maine. 1950s house through a -5 Fahrenheit night without running the heat pump at all coming from thermal storage, and not massive amounts of thermal storage. But that is another reason. Again, when we have peak rates, it may be less expensive to operate the boiler compared to operating a heat pump. And in Europe, there actually are controls on the market where you input the cost of fuel and the efficiency of converting the fuel to heat, and it will automatically switch between the heat pump and the boiler, the goal being lowest total operating cost, okay? Real quick on reducing water temperatures. 2 ways to do it. You can improve the thermal envelope, or you could add heat emitters. Improving the thermal envelope, I'm not going to spend a lot of time on it. There is a formula there, and there's an example you can look at. And there is a PDF file, right, Doug, that they can all these slides. I'm not going to have time to get through them all, but they're all available on the PDF. Real quickly, if I took 100,000 BTU per hour load down to 70,000 through building envelope improvements, that's just, I'm picking 2 numbers. I can reduce from 180-degree water temperature at design to 147 at design. And those 2 lines on the graph are just outdoor reset curves. Okay, so by improving the thermal envelope, you will bring the required water temperatures down. And typically that is easier than trying to add heat emitters. Going upstairs, so to speak, and saying we're gonna, you've got to move your furniture and we're gonna put a radiator here and all that, that's a harder sell, quite honestly, to a consumer than trying to, we could add insulation to your attic, so to speak. Again, I've got some slides here. I just want to stress to you one point, and these slides will give you later, when you look at them, the backup. I used to be of the opinion that if you had thin tube baseboard in the system, that you really shouldn't be using an air-to-water heat pump. And I base that on something that I know isn't true, and I think most of you know, is we only need 180-degree water in one of those systems at design load conditions. And that's about 2.5% of your heating season. The rest of that heating season, a baseboard system that needs 180 at design, it might need 120 when it's 35 degrees outside. So there's a lot of hours, and that graph in the upper left, that shows the bin temperatures for Syracuse, near where I live. There's a lot of hours when the outside air temperature is far warmer than your design temperature. And that's where even a high, quote unquote, high temperature distribution system with using outdoor reset can operate at much lower water. So the simulation results that I showed you, it shows you that you can work with a baseboard system and a heat pump. You probably won't get 100% of your heat from the heat pump, but you will still get the vast majority of the heat coming from the heat pump. Real quick, put the heat pump and the boiler in parallel, not in series. Don't put things in series, and hydronics is a good general rule to follow. With a conventional boiler, this is important. If you're going to take a boiler that has operated at relatively high temperatures and you're now going to modify the system to run at lower temperatures using outdoor reset because it benefits the performance of the heat pump, you need an anti-condensation valve on that boiler. If you don't do that, you will rust out that boiler and the vent system, okay? That's an important detail. Now, with a ModCon boiler, you don't need that. You want the boiler to condense. But as you go back and you look at these cast iron boilers that have run, especially in high temperature systems, there are different ways to do it, but the common way is a thermostatic valve. I refer to it as an anti-condensation valve. It simply mixes boiler water coming out of the boiler with return water to keep the inlet temperature to the boiler above the dew point of the flue gases. So we don't have sustained flue gas condensation, okay? Again, you can read these later. Here's another possible way to do it. This is using closely spaced tees. Notice that the heat pump is installed upstream of the boiler. There's a reason for that. We want the coolest water to go to the heat pump. If we flip the order around and the boiler was operating, it's going to elevate the water temperature so that the heat pump being downstream of the boiler is going to be forced to operate at higher temperatures. Remember what that does, it lowers the COP. Now, I put in red the key point. I wouldn't do this if it's a ModCon boiler, okay? I'd rather see a parallel arrangement because the lower the water temperature to a modulating condensing boiler, the higher its efficiency is going to be. Now, this is another piping method. Some heat pump manufacturers are promoting this. It's called direct to load, no buffer tank. It works. It's working based on a very high turn-down ratio on the compressor speed. You can run the compressor at a very low RPM, and there are companies doing that, literally turning a compressor on for 30 seconds and then shutting it off again. You might say, oh my gosh, that's a terrible idea. You're going to blow the capacitors, you're going to blow the contactors. Remember, these are not on-off compressors. These are inverter-driven variable speed DC motor compressors, essentially. So they can operate in cycles like that. And basically, they have a very wide range of heat output. They don't really need a buffer tank. With that arrangement, you see the boiler's tied in with a pair of closely spaced tees. It's downstream of the heat pump. I would do this, but with a caveat, and that is that the amount of outdoor piping is minimal. In other words, the heat pump's close to the building. You might have 3 or 4 feet of exposed piping because whenever there's heat going to the load, it's passing through the heat pump. And what you don't want to do is heat that water with a boiler, and then if you had 100 feet of poorly insulated exterior pipe, obviously you're going to lose heat there. So again, I'm going to jump through the notes just in the interest of time here. If you do have a long piping path outside, you can put in motorized valves and simply isolate the outdoor heat pump when it's off if you're running on the boiler, okay? Simple detail to do that. And yeah, real quick, there's a simple system, conventional oil-fired cast iron boiler, 3 zones. How do I modify it? Well, there's the air-to-water heat pump in parallel with the boiler. I'm trying to minimize disruption of the existing distribution system. Where can I do the least invasive surgery on the existing system and still respect that the heat pump should be in parallel with the boiler? Okay. Here's a ModCon going through a hydraulic separator, going to a low temperature radiant system, okay? There's the modification. Again, the heat pump and the boiler are in parallel. They each have their own circulator that would only run when that heat source is active. You need a check valve in each one of those circuits. So if the heat pump is running, we don't want flow reversal through the boiler. It just dissipates heat. And then the rest from the hydraulic separator out, nothing's changed. So essentially, again, heat pump and boiler in parallel. Here's an indirect tank with a couple zones in it, okay? There's the modification. Now, just to spice it up a little, I used a split system heat pump there instead of a monoblock. So again, no antifreeze requirement. It is tied in with a pair of closely spaced T's. Again, I'm trying to do minimal disruption of the existing distribution system. And then the boiler is tied in downstream of the heat pump. Okay, here's an injection. How many here have done injection mixing with radiant, variable speed injection? Still around, good method. We've done many systems with it. There's the modification. I've left as much of the existing piping in place and simply tied the heat pump in using a pair of closely spaced T's. And you could develop hundreds of slides like this based on what you're starting with. But the general concept is minimally invasive surgery, but keep the heat pump and the boiler in a parallel, or in this case, heat pump upstream, boiler downstream relationship. Here's a baseboard system, split system. Now, I've done pretty extensive modification. This is where I've added heat emitters, and I've converted the series baseboard system over to a parallel, what we call piping topology. We could do a whole 2 hours on this, but the bottom line is this. Series baseboard systems are not ideal for heat pumps. They're not really ideal for anything. I would rather go with a parallel arrangement of the heat emitters. Now you have independent balancing. You can create independent zones if you want. So what I'm doing is I'm strategically cutting the copper pipe at certain locations, and then I'm coming back with either PEX or PERT or PEX aluminum PEX and creating in this case, a four-zone distribution system from what was just a single zone series loop. And again, I'm using the hydraulic separator to tie it together. Okay? So again, I'm going to encourage you. I'm going fast through these slides. Doug hasn't pulled me down yet, but I could tell he's getting agitated over there. That's my last slide. I'll be around tonight. We're going to do the Q&A here starting in 10 minutes, roughly 10 minutes. I'll be happy to answer questions then. If you've got questions now, I'll hang around up front as we're setting up, but bring them to the Q&A. Again, thank you for the invitation to come up here and enjoy the show. Thank you.